Okay, good afternoon, ladies and gentlemen. My name is Sergey Loika. The topic of my presentation today is the capacity of Gaussian MIMO channels under interference constraints. I begin with a brief introduction to emphasize the importance of spectrum sharing. So it significantly improves spectral efficiency. It is widely used in modern wireless systems such as cellular, cognitive radio, heterogeneous networks, non-orthogonal multiple access, and so on. And it is a promising technology for 5G and beyond. However, there is always a problem with this approach as multi-user interference. Users making use of the same frequency generate interference to each other. So multiple input, multiple output or MIMO systems is a very powerful approach to control interference via antenna array processing. However, a few questions arise such as what is the optimal signaling strategy and what is the channel capacity. So for the standard Gaussian MIMO channels with no interference constraint, only the total power constraint or TPC, the capacity is well known and it is given by the celebrated log det expression, first obtained by Tsibakov in 1965, studied in detail by Telatar in 1995, and also his report popularized this area, which gained very wide acceptance in that time. So the capacity achieving input is Gaussian, the optimum signaling is on the channel eigenvectors, and the power allocation is given by the water filling algorithm. So if, however, we change a bit power constraint and instead of total, we consider per-antenna power constraints or PAC, or the joint power constraints, that Gaussian signaling is still optimal. However, the signaling on the channel eigenmodes is not optimal anymore. For PAC, we know the solution only in the MISO case. The general MIMO case is still an open problem, and the same applies to the joint constraint. So the feasible set or the constraints affect significantly the solutions we get. So if we add additional interference constraint, in addition to total power constraint, much less is known. We know that capacity achieving input is Gaussian. However, optimum signaling or transmit covariance matrix is not known in the general case. There are a number of numerical or algorithmic solutions using game theoretic approach, the dual problem approach, and many others, but no closed form solution in the general case. So in this paper, we concentrate on the analysis of the problem and on closed form solutions and their properties rather than numerical or algorithmic approach. So we obtain a closed form solution for optimal signaling in the general case up to dual variables, and we get completely explicit solutions for rank 1 and full rank cases. We demonstrate that there are major differences to the standard water filling on the channel eigenmodes. In particular, signaling on the channel eigenmodes is not optimal anymore. For example, independent signaling is not optimal for parallel channels. Optimal covariance is not necessarily unique. The total power constraint can be inactive and so forth. So we study the interplay of TPC and IPC and demonstrate that they determine interference limited and power limited regimes for which signaling strategies are quite different. We study the potential of spectrum sharing in a qualitative way via natural linear-algebraic structure of MIMO channels. And we also demonstrate that favorable propagation can be defined via simple run condition as an alternative to widely accepted definitions in the area of massive MIMO. We demonstrate that pre-whitening filter at the transmitter is optimal, and we also demonstrate the optimality of partial null forming in certain cases. We consider the standard Gaussian MIMO channel model with Gaussian noise, H1 is the channel. The capacity of this channel is well known and it's given by the celebrated log det expression. W1 here is just the channel gram matrix and I is the covariance of the transmitted signal. So the feasible set for R includes the total power constraint only in the standard approach. And then the optimal covariance is given by the celebrated water filling solution, where plus operator here retains only positive eigenvalues of the Hermitian matrix. However, when we add the interference constraints, the situation changes dramatically. So in addition to the main transmitter to receiver link, we have a number of links from the transmitter to primary users or simply external users in our systems. And we have to respect interference constraint for these users. In particular, the transmitter must not induce unacceptable interference to these users as expressed by this inequality here, where this is the actual induced interference power, and this is the maximum value of interference power. And I will refer to it simply as interference power in the sequel. Okay, so the constraint set is updated accordingly to include the interference power constraints as well. So the capacity of this channel is still given by the log det expression maximized over input covariance. However, optimal signaling is not known in general anymore. And that's simply because our feasible set has changed. So the optimal solution changes too. So the constraint set itself is not less important than the objective. Unitary invariance is lost due to IPCs, so the constraint set is not isotropic anymore, and the standard tricks such as Hadamard inequality do not apply. So in this theorem, we give the solution in the general case. As usually, one cannot see much from this general expression, so it will serve to us just as a tool to build up insight, to get more insightful solution in certain special cases, and to study the properties. I will only emphasize that this general solution includes an important part, which is a pre-whitening filter. So unlike the standard water filling solution, we have to do pre-whitening filtering in the transmitter. And if there are no IPCs, the pre-whitening filter reduces just to identity matrix, so there is no any pre-whitening here. So first we ask a question: when does the capacity increases indefinitely with transmit power? That's always the case with standard channel without interference power constraint, but does it still hold under interference power constraint? That is arbitrary large spectral efficiency of spectrum sharing is possible or not? While it's trivial under TPC alone, it's not trivial under the joint constraint with added interference power constraint. And this proposition gives an affirmative answer to this property, but there are conditions. In particular, the intersection of the null spaces of the interference channels must not belong to the main channel. Or equivalently, the null space of the sum of the interference channel matrices must not be in the null space on the main channel matrix. Then the capacity or spectral efficiency will grow indefinitely with transmit power under fixed interference power constraint. So this condition is if and only if, which means it gives the exhaustive characterization of all such cases. The next question we ask: when is the capacity zero? So which means no spectrum sharing is possible at all. This question has trivial answer under TPC alone. Either the channel is zero or total transmit power must be zero, but it's not trivial anymore under the joint constraint. So the answer changes quite a bit. We consider the case, of course, when PT is strictly greater than zero and channel is not zero. Otherwise, capacity is trivially zero. So, but in the standard MIMO case, these two conditions ensure that capacity is strictly positive. However, not so under interference power constraint. Its capacity is zero if and only if sum of the interference powers must be zero for some users, and the null space of the sum of W2s for those users must be in the null space of the main channel. So the relationship between null spaces of different channels here is critical, as you can see. Okay. So, and zero interference power, of course, is equivalent to zero forces required, zero forcing required for some users. As a simple corollary, if the rank of the main channel exceeds the rank of the sum of all W's, then the capacity is not zero for any interference powers, including zero, and it grows unbounded with the total transmit power. Therefore, we can say that this rank condition represents favorable propagation scenarios for spectrum sharing, which is possible for any interference requirement, including zero interference, of course, and when arbitrary large spectrum efficiency is attainable given enough power budget. It remains to be seen whether this condition holds for massive MIMO or not. So next, we study the rank of the optimal covariance matrix. We know well that in the regular MIMO case, the rank of the optimal covariance is upper bounded by the rank of W1, the main channel. Is it still true under interference power constraint? And the next proposition gives an answer that yes, it is true, but under certain conditions only, not in general. In particular, if the TPC is active and the sum of all active W's for which the IPCs are active is a full rank matrix. Then yes, this condition is true. Otherwise, it doesn't hold. In general, R star may not be unique, so there may be several optimal covariance matrices, but among those matrices, there exists at least one which satisfies this condition. So it's interesting to know that R star may not be unique under the joint constraint, which is in stark difference to the TPC alone, where R star is always unique. So as a simple corollary of the rank bound, if the rank of the main channel is 1, then the rank of optimal covariance is also 1 under the stated conditions. So that's exactly like the standard water filling. However, signaling on the only eigenvector of W1 is not optimal anymore under the joint constraint, unlike the TPC alone. So what is this optimal signaling is then? So here we consider rank 1 case in detail. W1 is here. So there is only one active eigenvector and only one non-zero eigenvalue. We consider the case of only one primary user. Gamma I is interference to signal ratio, and gamma 1, gamma 2 are the thresholds for this ratio. So in low ISR regime, when gamma I is less than gamma 1, the TPC is redundant and the optimal covariance matrix is here. So the capacity expression is very much familiar, except for the extra term, which we name here SNR loss, which quantifies the loss in SNR due to enforcing the interference power constraint. So what we observe from this expression is that beamforming on W2 pseudo-inverse times U1 is optimal, but not on U1. So W1 pseudo-inverse plays here pre-whitening filter, role of pre-whitening filter at the transmitter. And if there is no IPC, it's simply the identity matrix, so there is no any pre-whitening. So we could see that IPC affects significantly the optimal solution for optimal covariance matrix. In moderate ISR regime, when gamma I is in between gamma 1 and gamma 2, we see that a similar solution applies, except for W2 pseudo-inverse, we use W2 mu, which includes W2 plus identity matrix. Again, beamforming on U1 is not optimal here. We have to beamform on this vector, and W2 mu inverted here plays a role of pre-whitening filter at the transmitter. And finally, when ISR is large, or when U1 belongs to the null space of W2, then the IPC is redundant and the standard water filling solution applies with optimal signaling on the only active eigenvectors of the main channel. There is no SNR loss. So beamforming on U1 here is optimal, and there is no need for pre-whitening filter in this case. So here is an illustration of this solution. There are 3 different regimes: high SNR beamforming on U1, moderate ISR when there is an interplay of IPC and TPC. We cannot beamform on U1 anymore. We have to beamform on this vector, which changes the direction. And in low ISR regime, only IPC is active. And again, we cannot beamform on U1. We have to beamform on this vector. Okay, so the presence of interference power constraint makes these two solutions quite different from the standard solution, which is beamforming on just U1. Likewise, we can obtain full rank solutions. I will not go into all the details. I will just demonstrate that sometimes solutions are similar to the standard water fillet, but there is still pre-whitening filter at the transmitter. I think that's a common conclusion from our studies, that whatever we impose interference power constraint, we have to use pre-whitening filter at the transmitter to satisfy that constraint. So in moderate INR regime, when SNI is large and interference to noise ratio is moderate, when the W2 of rank 1, the optimal covariance is given by this compact expression. Again, these first two terms are effectively the standard water filling terms. And the last third term is a correction due to interference power constraint, which is known in the adaptive antenna array literature as partial null forming. So therefore, our result here demonstrates that partial null forming is also optimal from information-theoretic perspective in the context of spectrum sharing. This is a rigorous proof of the technique widely used in the adaptive antenna array literature without any information-theoretic considerations at all. But of course, this optimal result applies only under certain conditions, not in the general case. Okay. So in conclusion, we have considered Gaussian MIMO channel under interference constraints, which are important for cognitive radio, spectrum sharing, conventional cellular system, heterogeneous networks, non-orthogonal multiple access, and so on. We address the issue of optimal signaling or optimal covariance matrix at the transmitter. We studied the general properties such as arbitrarily large spectral efficiency or unbounded growth with transmit power, zero spectral efficiency when no spectrum sharing is possible at all. We studied qualitative behavior via the linear-algebraic structure of null subspaces of MIMO channel matrices. We defined favorable propagation via the simple rank condition, which can serve as a valuable alternative to the definitions used in massive MIMO systems. So we obtained explicit closed form solutions for rank 1 and full rank cases. We demonstrated the optimality of pre-whitening filter at the transmitter and the optimality of partial null forming under certain conditions. And one of the interesting conclusions that independent signaling is not optimal even for parallel channels. So thank you very much for your attention, and that concludes my presentation.